World over, 350 million people aged more than 65 suffer from arthritis. When these people rise from a seated position, a large portion of their body weight is taken by the knee. This is a container which is available at the Indian Institute of Science, Bangalore. The lid of the container is bistable in nature. When pressed from the top, the side teeth displace outward, thereby allowing the container to be opened. The lid is now in its second equilibrium state. To close the container, the teeth are laterally pressed, which bring the lid back to its first equilibrium state. Interestingly, the lateral force needed was 40% of the vertical force needed for actuation. The BiStable lid was simulated in Abacus to recreate its working. Nonlinear analysis were carried out in Abacus on a 2D model and its extrusion to understand the nature of the boundary conditions that need to be adopted in our chair. Both simulations successfully capture the bimodal bistable nature of the lid. Next, we looked at a few profiles for the top surface. A single cosine curve without a central stiffener failed to display bimodal bistability and hence was eliminated. The difficulty of incorporating a flap led to the elimination of the two cosine curve profile. Having the lowest value for mode 1 actuation, the cosine curve with central stiffener was deemed the most suitable profile. To physically impose the required boundary conditions, pivot holes were provided to constrain the in-plane motions. The Abacus simulation, as seen to the top right of the screen, captures both modes of actuation. The COMSOL simulation, as seen to the top left of the screen, shows a sudden transition from one equilibrium state to another at a force value of 1.85 Newton. The same characteristic displacements of the profile were obtained when it was physically actuated, thereby validating the above simulations. Next, we try to simulate the mechanism by integrating it with a bell crank. The transfer of force was difficult to simulate in Abacus as the bell crank is a rigid member and not a deformable one. To overcome the difficulties, an equivalent rigid body simulation was conducted in Adams. The video seen on the left of the screen corresponds to the mode 1 actuation, that is, when the person is sitting on the chair. When the person wants to rise, a force applied on the armrest corresponds to a mode 2 lateral force through a bell crank, as seen in the video to the right. This brings the mechanism back up to the initial configuration. The bimodal bistable mechanism and the bell crank actuation were integrated to arrive at a final design of the chair. The prototype of the same was physically tested for its functionality and hence proved its feasibility. To conclude, the highlights that outline our project are the following. Thank you.